Hi, my name is Dawn Andrews. I'm from Lab Group E1 and I'm presenting Lab 4, Combustion Dynamics in a Reiki Tube. This experiment will be looking into the frequencies and amplitudes of the oscillations caused by the combustion reaction. It will also be a demonstration of the Reiki Tube itself, as well as several other types of measurement tools used in the experiment. On this next slide, we see a video of the Reiki tube, which was invented by Professor P.L. Reiki when he discovered that a heat source in the lower half of a tube could produce audible sound waves because of the way that the resulting pressure oscillated. These oscillations are visible in the slow motion video to the right, and during the course of this experiment, we will be investigating the properties of this periodic behavior. The focus of this experiment will be an investigation into the amplitude, frequency, and phase angles that result from different heat source locations. We will also be able to gain a deeper understanding of the other equipment involved. On this next slide, the experiment was held in the ESM Building Combustion Lab, which is home to a 6-foot Reiki tube. This Reiki tube is attached to a pulse combustor as the heat source and has a few different methods of measuring the combustion dynamics. There are 3 piezoelectric transducers located quarterly along the length of the tube. There is a photomultiplier that faces a window to observe the light energy released by the flame's chemical reaction, and there is a rotometer that measures mass flow rate of fuel into the combustion process. We will be taking measurements at 4 different key locations, which are explained at the right. We will also take measurements of the fuel flow rate and where the tube starts and stops making noise as we move the heat source up and down. The tables on this next slide show the amplitude and decibels of the sound produced by the tube. These calculated values are very, very high, but the locations show the trend that we should expect. The loudest volume comes from the optimal location, location 1, and drops as you move farther from this spot. These values were initially measured in voltage in the raw data. They were converted back to pressure using our Reiki tube's calibration trend and then calculated relative to the hearing threshold. The raw data was obtained from the piezoelectric crystals, which basically intake a pressure and output a measurable voltage. On the right-hand side, there is a calculation of the ideal resonance frequency for our tube. The first equation, F equals A over lambda, is a standard wave equation from Physics 2. We make the simplification that lambda is equal to twice the length of the tube, or in other words, that our standing wave is half of a full wavelength. The second equation, A equals the square root of gamma RT, is from thermodynamics and measures the speed of sound in any fluid. For air, gamma, R, and T are all standard values, and therefore frequency can be solved from the combination of these two equations. The resulting frequency is 93.74 Hz, which matches the measured frequencies in the Reiki tube for our ideal case at location 1. The slight difference can be explained simply because our calculated value uses ideal air conditions for the temperature, humidity, and other extraneous factors. The other experimental values in the second table continue to show the trend that location 1 is the most ideal position. For location 4, the photomultiplier value is an extreme outlier that was probably caused by an outside factor, and it is disregarded in following the trends. We continue the data analysis on the next slide by finding the phase angles relative to pressure sensor 2. It is located in the very middle of the tube, and therefore it should theoretically be exactly at the antinode of the standing wave. The standing wave seen in the diagram at right helps to visualize this. We can also place P1 and P3 at 1/4 and 3/4 of the way down the tube respectively. In a perfect standing wave, our P1 and P3 values would be near to 45 degrees. This is consistent with the data from location 1. Out of curiosity, I carried the same phase angle calculation into trial 3 when the burner is 2 inches off from its ideal position. As you can see, the phase angles are drastically affected by this movement, and it knocks our standing wave nearly out of phase. When moving the burner farther back up, sound disappears altogether at 6.4 and does not return on the way back down until reaching 4.1 inches. On this slide, I also did out the calculation for mass flow rate of the fuel as best as I could with the values we had. The mass flow rate equation can be simplified because temperature difference is negligible, and the chart in the lab handbook eliminates the need to find the specific gravity for the float. With given values for all numbers except for PR, which I researched and estimated at 144.7 because that's the pressure coming out of a standard propane tank, we end up with a flow rate value of 74.05 standard cubic centimeters per minute. On this last slide, the conclusions of the experiment are as follows. We were able to demonstrate the Reiki tube's ability to produce sound from the pressure waves caused by heating the air at a quarter length from the bottom of the tube. And we were able to justify that this was the ideal placement by analyzing the trends in the frequency and amplitude charts and by explaining it to the ideal calculated value for the tube's frequency. We also looked at the relative phase angle calculations and saw how the standing waves were stronger or weaker based on the location of the heat source. Finally, we were able to calculate the flow rate of fuel into the tube in order to understand how the rotometer functions, and also that safety was key to this lab. While our results were consistent with what we expected to see based on the theory of sound waves, error can still be accounted for. The Reiki tube had been in operation for a long time, so it was very hot, and temperature could have played a role. Another significant source of error is the atmospheric conditions. We ran this experiment on the morning after a big storm had hit, so humidity, barometric pressure, and temperature conditions of the ambient air were less than regular. One last possible source of error could be that the Reiki tube was struggling to intake enough air to maintain a flame. We placed a fan underneath it, but the fan's oscillations partially transferred to the pressure fluctuations in the tube. Despite all this, the results do follow the correct and expected trends, and the experiment was successful in demonstrating combustion dynamics in a Reiki tube.